right, hello everyone. My name is Andrew Harris. I'm a member of the professional staff at the Johns Hopkins University Applied Physics Laboratory, and I am giving a talk on the introduction to SMT solvers with applicability to flight software development. So I'm currently the flight software lead for the Dragonfly mission. I've worked quite a few missions in the past, so like Kelly said in the in the keynote yesterday, I've been around for quite a while. I worked on a mission called Contour, the Messenger, Mercury Orbiter, the New Horizons mission to Pluto, Solar Probe Plus, Mars Perseverance for a while with Eddie, and DART with Chris and Luis, Dragonfly with Brandon and Luis. So I've been around for a while. And I just wanted to say, enjoy. It goes fast, so enjoy the time that you're working with each other, and it does go by fast. And enjoy everything, including when you're trying to debug your equipment that's either on the moon or out there 47 years later. So I wanted to start just by saying I'm going to describe a tool that exists. It's called Z3. It's a product made by Microsoft Research. And it's what's called an SMT solver, and it's a very complicated name, but basically it can be used to solve complex sets of constraints over Boolean variables, bit vectors, integers, and other data types, and I'm going to try and show some extremely simple examples here. The term satisfiability modulo theories, my understanding is it's kind of a SAT solver, which has been around for a long time, which was limited to solving kind of complicated Boolean formulas, a program which could accept a Boolean formula with many Boolean variables, and it would give you a set of assignments to those Boolean variables where the Boolean formula was true. And SMT solvers are kind of the same thing, but plus additional theories like integer arithmetic, bit vectors, and general integers, as well as real numbers. So it's basically satisfiability, including additional theories, or satisfiability of an integer formula in the context of integer arithmetic, and they just use the word modulo in that context for some reason. I'm not sure why, but it's a complicated name. There's a URL there if you're curious about Z3 itself, and it has a set of Python 3 bindings which make it easy for humans to use, and I'll give you a few examples of that in the slides. It's also open source and MIT licensed, so you can use it yourself with a flexible license. So I wanted to start with kind of a really simple example. And you really wouldn't use Z3 for this purpose or only for a slide like this, but it gives you just a brief introduction to how you can think about it. As I said, it can solve sets of Boolean equations. And for example, there are many real-life physical objects that can be represented by either being in one state or another, or for example, propulsion valves or switches or relays. And Claude Shannon, back in the 40s, wrote a master's thesis where he discovered kind of a correspondence between electromechanical relay networks and Boolean algebra. And this was considered to be the most important engineering master's thesis of the 20th century. So since we can stand on his shoulders and, for example, use Boolean algebra to represent sets of networks of propulsion valves or switches, for example. So in this first case, we have a Boolean expression A and B, which can represent a pair of valves in series. So valves are open, and we represent that by true, and if the valves are closed, we represent it by false. So this basically says A and B, the Boolean expression represents the series valves where if the expression A and B is true, then fluid or liquid could flow through the valves. And we have the same case for parallel valves, which would be represented by A or B. So in Z3 with the Python bindings, you can declare A and B as Boolean variables, and then you can ask Z3, can you find a condition where my equation A and B is true? And Z3 will say, yes, I can for you. You have to just set A to true and B to true, and your equation A and B will be true. And then for the OR case, you can write a simple version in Python. You can say, can you find me a condition where my equation A or B is true? And it will say, yes, I can. Just set A to true and B to false. So that's kind of like a very simple way of interacting with the Z3 and the Python bindings. And you can do this for more complicated sets of valves, for example, way more complicated than this. This is still an embarrassingly simple use of Z3, for example, but you can ask Z3 to solve a more complicated equation. Here, I'll just step through briefly. On the lower case here, it's the slightly simpler path. So we have several valves in series. We have, and in series, we define it as an AND operation. So we have valve L, and then I describe valve M here, which I just put a hash through to say, for example, if the valve has the opposite behavior, if it defaults to closed or open, for example. And you can record that as not M. And then there's a pair of parallel valves in an O, which are an OR statement, and then P and K are also in series. So that covers this path, this lower path. And similarly for the top path, you have A, and then a parallel setup with B, an OR of D and E at the top, and then not G is that path. And then you describe this path as not C, F, not J, and K. So you basically can describe the network of Boolean variables in whatever configuration you have, and describe it in the Python with the Z3 bindings. And these are actually data structures. So these are actually Python objects, and you can create these programmatically. So if you have a network that you want to create that's way more complicated than this, you don't have to type this in. You can actually programmatically construct this really large kind of Boolean formula. And then you can ask Z3, can you find me an example where this Boolean expression is true? And it says, yes, I can find you a path where fluid would flow through these valves. For example, if L is true, if you open L, and you open N, and you open P, and you open K as well, and then you close M, which is kind of the opposite polarity, basically your fuel will flow through. And you can also say the same type of formula, but then you can attach additional constraints. So for example, if you want to say, okay, but now my valve K is shut closed, it will never be able to open. Can you help me solve this problem? And Z3 will come back and say, yes, you can open A, B, E, and close G, and then you'll have your fill. So just an example of using Z3 to help you solve kind of Boolean formulas, which is kind of from its prehistory as a satisfiability solver over Booleans. But Z3 includes bit vectors as well, and these can be used to model machine integers. So I wanted to show a couple things in this slide at once, but one of them is to just show you how you might be able to think about a snippet of C code, for example, and kind of codify it into Z3 manually if it's small enough and you want to do it quickly. You can do that. So this is an embarrassingly simple C function here, or C statement. We have a variable x. Well, it's a signed integer, 8-bit integer. And we have a simple if expression where if x is less than 122, we add 5 to it. If not, we add 1. And we can ask Z3 questions about this code. So we can ask, is it always true that x will be bigger at the end of the if statement? And if you formulate that correctly to Z3, it'll say, no, that's not true. If you set x to 127, it'll violate your condition. And just because signed integers, if you add 1 to 127, it'll be 128. It will wrap over to 0, so x would be smaller. So the question is, how can you formulate that in Z3? Well, Z3 has, as I said, bit vectors. And so you can create a bit vector of 8 bits in width. This is a signed bit vector. It also includes unsigned bit vectors. And you can codify the Boolean condition of your if statement as kind of a Boolean expression here, x not less than 122. And we, I think by convention, if you're doing this sort of thing, you call the variable x not before the assignments and x1 afterwards. And you basically codify the right-hand side of your then expression, so x naught plus 5 and x plus 1. And then Z3 provides you with a more sophisticated kind of constraint object, which is essentially a conditional constraint, and it's called an if-then-else. And you basically tell Z3 to construct that out of your condition, out of the right-hand side of your then expression, and then the right-hand side of your else expression, and you assign the result of that to the value of x after the if statement finishes. And basically, this allows you to describe conditional constraints also within Z3 that it will be able to reason about. And then you can ask Z3, can you find me a condition where x1 is less than or equal to x naught? So basically, kind of, can you find me a condition where I'm not expecting to see this condition? And typically what you do is you reverse the predicate you're actually asking for. And Z3 will chew on that for a while, and if it comes back that it's satisfiable, you can, which means it was able to find a case where x1 was less than or equal to x0, then it will give you that answer. So you can go back and you can actually modify your code and interact with it and then keep trying. And if it keeps finding examples of cases where that may be the case, you can continue to fix it. And at some point, it'll come back and say it's unsatisfiable. And that basically means Z3 has proven that there's no assignment to x naught that would ever end up with x1 being less than or equal to x0. And in that case, you can also basically, what's a good way of describing it? The dual of that is also true. So there's actually no, then you can, that helps you answer this question as well, where x is always bigger at the end of the if statement. So basically, another way of saying it is, there are two ways you can use Z3 that you can keep in the back of your mind. One is to ask questions about satisfiability, which are questions about, is there a single assignment of my variables that results in the formula being true? And there's also the question of, with this formula, are all assignments to the variables do they always result in true? And that's a question of validity. So you can ask both questions and you just use Z3 in a different way. So if you're asking about whether your formula is always true, you can basically invert your formula. And then if you get a result of unsatisfiability, then you can argue the dual of that. So that's kind of an example of bit vectors. The notion that bit vectors can wrap around. You can have signed and unsigned bit vectors. There's a lot of, basically all of the bit vector operations are supported by Z3. So reasoning about addition and subtraction and shifting and ANDing and ORing are all supported. So it's quite useful for kind of program verification purposes. And there are tools, I have not used them. I'm not an expert on SMT, but there are tools that you can use to automatically generate Z3 formulas from pre-existing C code. So if you have a question about any of those, let me know. But the idea here is, if I can give you kind of an intuitive idea, or basically a simple way of just hand coding, interacting with Z3 yourself, you don't have to learn a whole new tool if you're just doing something simple. And the Z3 instructions have a couple of really good examples. One is if you want to write a test in C for a quick way of deciding if an integer is a power of 2. And there's like an optimization trick to that. I think it's like if x and x minus 1 are 0, then it's a power of 2. And you can code that up quickly in Z3 and you can do proofs on it, basically check if that condition is true. And there's also other interesting small examples in there in the Z3 instruction and documentation. So it's kind of interesting to read about. So in terms of integers, this is a bit easier to grasp, but you can basically ask Z3 to reason about constraints on integers. So for example, if you have a set of 3 integers, you could ask Z, give me a configuration of these integers where they're all distinct, they're all greater than 0, and x is less than y, and y is less than z, and y is greater than 20, and Z3 will come back and give you a binding of those. So that's a simple example of using integers and solving integer constraint problems. So when I saw this, I had been experimenting with Z3 on my own a little bit before this, but we wanted to come up with a way of describing thread priorities for our real-time tasks in the Dragonfly flight software. So I went out and dusted off my Z3 hobbies and thought about describing thread priorities as Z3 integers and using constraints on the priorities and encoding them in Z3, just like I showed on the previous slide. So we could describe all of our tasks, describe constraints between them, and let Z3 come up with a solution where all the constraints for the priority assignments would be satisfied, or not, depending on the configuration that we were requesting. So I have an example on the next couple slides where we are going to just go through a simplified version of what we're doing for Dragonfly flight software, and we'll just go through the Python program. So here's a simple example. Imagine, in all of our real-time operating systems, we have a fixed set of finite priorities, maybe 0 to 255, for example, for many RTOSes. But in this example, we can just say our priorities are between 1 and 30. So we can define just Python variables for that. We can define a function called thread that allows you call it and you pass in the solver that you're using. And I'll show you that on the next slide. And also a name of the thread. And then it will create a Z3 integer, and it will kind of predefine two constraints for that integer. One is that the integer has to be greater than your minimum priority bound. It has to be less than the maximum priority bound, and then it will return that integer object. And so you can call that on a number of threads. So for example, we have 4 threads here. We define them using that function. And then we can ask we can add a constraint into our solver saying the thread priorities should be distinct. That thread A should be greater than B. Thread B should be equal to priority 15 for some reason. And thread C should be greater than both A and B. Oh, and by the way, also D should be less than 10. And then you can call Z3 on that. And here's kind of a full example of it. So we import Z3, and then we have the code to define our thread function, the code I just showed on the previous slide here, and then we can ask Z3 to check that model, and if it comes back as satisfiable, we can get the model from Z3 and we can print it out, and Z3 will come up with this configuration of thread priorities where all your constraints are met. So you can use a technique like this to, maybe in a non-traditional way, help you describe a problem in your own domain. For example, for us, we were interested in using it for describing our thread priorities. And the overall, I wanted to say that Z3, it's a really powerful tool. And these examples are really small. I've personally used Z3 for solving as a hobby, kind of asking it to solve problems of 800 or more Boolean variables at once, and it has no problem with that. So these are really simple examples, and it's used across industry, and it's used as a foundational tool for a bunch of theorem provers. Lean theorem prover uses it in the background, and there are a lot of tools that target Z3, I think, including bioinformatics and all kinds of things. So it's a really powerful tool, and if you're interested in experimenting with it, I would highly recommend it. I wanted to show an example of kind of describing a thread priority allocation just using the simple integer constraints. And, sometimes, well, the reason I thought it was a good idea is because it kind of gives you a way of specifying your thread priorities as kind of almost like a formal specification. This Python code, it allows you to explicitly describe the motivation for why the priorities are the way they are in your system. And, David in the keynote today, after your system has been up there for 47 years, we keep a version of this in our source code control system. So this is basically another program that's in our source code tree. And we can always look back and say, okay, well, we have these constraints on our priorities. We know this one needs to be higher than that one. And when your mission has a 6-year cruise phase, that'll help. That'll help with maintenance in the future to allow people to see what was the justification for why your priorities are the way they are. And, I worked on New Horizons too, where we had a 9-year cruise. So I've had previous experience with that as well. So I always try, I think, try and keep in mind, like based on the previous one, just try and document everything you do as well as you can. And that'll help down the line. And again, there's the URL for Z3. So if you're curious about it, take a look at that URL. If you stop me in the hallways afterwards, and if you have questions about whether it might be applicable to you, I'm happy to talk about it. So thank you very much.
All right, thank you, Andrew.
Yep.
Any questions in the room? Perfect.
I wrote this question down, so please bear with me. Does the absence of a solution imply unfeasibility?
I'm sorry, can you repeat it?
Does the absence of a solution from Z3 imply infeasibility or unfeasibility?
I believe so, yes. If it returns unsatisfiable, there's no allocation to the variables that can satisfy. Okay. Yeah, you're welcome.
Hi. And do you think, is there any way to include deadlines to your example? So the distribution of the three priorities can be done automatically?
That's a good question. That's a good question. I think it's beyond my skill level to do that. I'm just a modest flight software developer. I thought about it a little bit, but I wasn't, yeah, it would require more effort on my part for sure. But it's, they are, I think you could consider them, constraints in some way. So yeah, it's definitely a possibility. Yeah.
Eat the mic. I have a question, if it's all right. So I was a bit curious. Are these like table or these rules based equations Z3? Is it deterministic, and also is it optimal? Like the solution it provides, is it the best solution or is it a solution?
It's a solution, and it is deterministic. So when we run it with the same inputs, we do get the same outputs for the priority allocations if you run it with the same inputs. So I'm not sure that's always the case for all the theories. There might be some random seeding in it, but from our observations, we always get the same allocations with the same input file and the same. Okay. Okay, so Pierre says it. Okay, all right. Talk to Pierre.
So I wanted to ask, can it tell you the number of solutions or just that one exists?
I don't believe it. I'm not sure. I haven't found a way to get a number of solutions. I think
Yeah.
it's just happy enough to give you a single one.
Okay.
Because that's basically the notion of satisfiability, I think. Yeah.
Is there anything that can error check the constraints that you add to the solver, such as if you happen to have set the thread has to be less than 10, and then later you say the thread has to be greater than 10?
No, there is none, and it's the human's responsibility to define those constraints correctly. So that's another one. Make sure your specification is right. That's a good question.
Thank you.
All right, we're going to take one from Slack. From Lir Atias, how does Z3 work on the back end? I.e., what is the logic or methodology it uses to perform the solve?
That's a good question. I do not know. And it depends. I know it varies on the different theories that are there. Obviously uses different heuristics, but I am not sure myself. I treat it as a black box. And the Python bindings make it accessible to normal humans to use. So yeah, I'm sorry I can't give a better answer to that one.
That was a good answer. All right, thank you, Andrew. Round of applause.